class, we are now going to look at Lewis acids and bases. In the last chapter, I'm going to briefly go over acid rain. So we've pretty much covered Bronsted-Lowry and Arrhenius acids. Bronsted-Lowry has to deal with protons. So one is a proton donor and the other is a proton acceptor. Now we're going to confuse it even more with dealing with Lewis acids and bases. This expands on top of what a Bronsted-Lowry model, which enables no other compounds that normally wouldn't qualify under Arrhenius and Bronsted-Lowry, but will qualify under Lewis acid-base theory. So a Lewis acid-base theory focuses on the transferring of an electron pair. So this has to do with the electron pair here. So if you look at this, Bronsted-Lowry focuses on the proton and where the proton starts and where it finishes, but the Lewis model focuses on an electron pair. Lewis acid is a lone pair acceptor, and the Lewis base is a lone pair donor. So in this case, this is a lone pair donor. This is a Lewis acid. It is a lone pair acceptor. The H has taken the lone pair on the ammonia, but it doesn't necessarily require a hydrogen ion. So this is why it expands on Lewis acid base and allows compounds that would not necessarily fit into the Arrhenius or the Bronsted-Lowry model. A Bronsted base is a proton acceptor because it has a non-bonding pair of electrons. So if we see here, we have a non-bonding pair of electrons, which it has to have in order to be a Bronsted base, in order to accept the proton. However, if we look at a Lewis base is an electron pair donor. This is a donor, and the Lewis acid is an electron pair acceptor. So this has to have an empty orbital to allow to take in these electron pair. So this is a Lewis base, which is again electron pair donor, and this is a Lewis acid, which is an electron pair acceptor. All Bronsted acids and bases are all Lewis acids and bases, but not all Lewis acids are Bronsted acids. And that's because not all Lewis acids will have a proton. So Lewis acids, they are electron deficient, meaning they don't have a full octet or are being attached to electronegative atom because they have to take electron pair into an orbital. They must have an empty orbital in order to accept an electron pair. For instance, a proton has an empty 1s orbital. The boron in BF3 has an empty 2p orbital and an incomplete octet, so it can accept a lone pair. Many small, highly charged metal cations have empty orbitals because they have high oxidation states, and they can be used to accept electrons. And atoms that are attached to highly electronegative atoms and have multiple bonds can be Lewis acids. Lewis bases have electrons that are willing to give away or share with another atom. The Lewis has to have a lone pair in order to make to donate. The Lewis base must have base must have a lone pair. It can donate. Anions are better Lewis bases than neutral atoms or molecules. So in this case, an anion is a better base than a neutral molecule, is what it's showing. And generally, the more electronegative an atom, the less willing it is to be a Lewis base. So this is more electronegative, so it doesn't want to be a Lewis base. Okay, so the base donates a pair of electrons to an acid. And what it does is it forms a bond. So it creates a compound, and the product is called an adduct. So this is a synthesis compound. Remember, A plus B equals AB? That's what this is. It's a synthesis compound that it creates a bond between these two with that electron pair. So Arrhenius and Bronsted acid base reactions are also Lewis reactions. So you can see we have this here. We have a lone pair. The lone pair comes in, and let me make sure. Nope, sorry, I'm on the wrong thing. I'm like, that doesn't seem right. Here's the lone pair. It attaches, and you can see that it is attached. There is a bond now, which has created a bond between these two compounds. Same thing here. If we look, we have a lone pair here. It positions itself to create this bond with this other compound. Okay, so the definition of acids as acid pair acceptors broadens the range of what can be considered as an acid. This is why this is here, because Bronsted-Lowry follows a proton where it starts and where it ends, and this can now expand with acids that don't have protons. A Bronsted acid is a proton donor, but the proton itself is a Lewis acid and not the molecule it came from. So we're looking at we only look at the H itself and not the molecule it was attached to. Bronsted acids react with Bronsted bases to produce a salt and water. However, this is where Lewis adduct, it creates a single compound that results from a synthesis. So this is an A plus B equals AB. All right, so let's do a breakdown of these and determine whether these are Lewis acids, Lewis bases, or neither. So I'm just going to go over them with you. So this first one is iron 3. It has a high oxidation state. So it is a small, highly charged metal cation, and it has an empty orbital, so it can accept electrons. This is a Lewis acid. Now we have methane. Methane, first of all, is nonpolar, which has nothing to do with it here, but it doesn't have any reason to react, is what I'm trying to say. It has a filled octet around the carbon. It has filled duet around the 4 hydrogens. So this has no play into it being a Lewis acid or a Lewis base. It's neither. Now we look at chloride. Chloride has a lone pair on it that can bond. It can donate to a Lewis acid, so it is a Lewis base. And ammonia, even though it's not shown here as well, has a lone pair on it, and it is also a Lewis base. It can donate that pair. Now hydrogen, this is a filled duet, so it's not going to do anything. It's stable in the way that it is, so it's neither. And iron by itself, not in an oxidation state, means it's a solid, and it's not going to do anything either. Okay, so formation of an adduct. So here, this is a perfect example of A plus B equals AB. Now, as we can see, the Lewis base donates that lone pair. Lewis acid accepts that lone pair as long as it has an empty orbital to take them, and the Lewis base has to have electron pair to donate. This comes together to create a single compound, a synthesis compound. Here, excuse me, or a combination compound. It produces one compound. This is a Lewis adduct. Okay, so Lewis acids and bases have different strengths. For example, ammonia and nitrogen both have non-bonding electron pairs that can be donated. However, non-bonding nitrogen are held much more tightly and less likely to be shared. So, with an electron pair acceptor, but nitrogen has a lone pair and it will share them, so it is a stronger Lewis base. Lewis acids must have an incomplete octet or a duet for hydrogen in their valence shell. So as these Lewis acids, where we've only dealt with protons before, now we can look at something like boron, which only has 6 electrons and can be considered a Lewis base. When a Lewis adduct forms, both electrons shared in the new covalent bond that comes from the Lewis base, so we can see these come together. That is now called, this bond that's been created, that's right here, is called a coordinate covalent bond. So yes, it creates a Lewis adduct, that is the compound, so that's the synthesis compound, but the bond that's been created, coordinate covalent bond. And Lewis acid-base reactions can take place in any physical phase. All right, so let's look at some examples. Metal ions act as Lewis acids when they form hydrates in solution, because they can take they can accept the lone pair off of the hydrogen, and that makes this aluminum in this case a Lewis acid because it can take it. It's a high oxidation state. It has room for that. Now, something we haven't really discussed: compounds with double bonds can often shift those double bonds to pair with one atom as a non-bonding pair, leaving the other atom as an unfulfilled outer electron shell. That may not make sense, but let's look at this. CO2 reacts with water to form a Lewis adduct, carbonic acid, which then undergoes ionization as a weak acid. And I think I have it here. Okay, so CO2 reacts with water. It forms a compound, one compound. Then it undergoes ionization as a weak acid. But the double bond is what they're trying to show here from this second paragraph, is that, remember, these are electrons. They can move. So this has room to move these electrons to, in a sense, to be pushed up. And when it's pushed up, now it only has one bond, but it can take 6 electrons around it. There's actually a charge on this side, but it's not drawn with the charge. This is a neutral. This has a charge on it. Remember in Chem 111, you should have learned about formal charges. This has a charge on it. So it has the ability to do this in order to make room for the next move. So here, This is what it's talking about. Let's go back. Which then undergoes ionization as a weak acid. So what does it do to make it a weak acid? And what's a weak acid? So let's take a look here. We have a lone pair that comes in, and it attaches itself to the carbon, but it can't attach itself to the carbon because this is a filled octet. However, the double bonds, one of the double bonds can move, and once it moves, it leaves 2, 4, 6. It leaves 6 here, and then it's creating a new bond with that new electron pair. So it pushes the electrons up, and oxygen can handle this. It's still stable in this way of doing things. By the way, if you're into organic, this is what you're going to be doing. You will be drawing a lot of things like this over and over again. What do I mean? It means that you will have to show when something comes in, what's the next step, what happens the next step, and what happens the next step. You will have to continuously draw this stuff. So this is very similar to organic chemistry. This is going to come in. It's going to push this up simultaneously. When it pushes this up simultaneously, it's going to now orient itself with the hydrogen here. But this hydrogen is going to take this ionizable proton off of it. When it pulls that off, it's going to simultaneously cut the bond that's here. So this lone pair stays here. This hydrogen goes to this oxygen, and it makes it a carbonic acid. That proton is highly ionizable. Okay, so Lewis acid is a species that is able to accept an electron pair from another chemical species. That forms that bond. That would be an adduct, but that bond is a coordinate covalent bond. A Lewis base is a species that is able to donate a lone pair or non-bonding pair to another species. Again, that forms a coordinate covalent bond. A Lewis acid-base reaction occurs when the Lewis base donates a pair of electrons to an acid, creating a coordinate covalent bond in the process. That product of the reaction is called a Lewis adduct. All Bronsted bases are Lewis bases. Bronsted acids must be proton donors, but Lewis acids do not have to have a proton or donate a proton to be considered an acid. So Lewis acids include many species that would not qualify under a Bronsted acid. All right, and now we're on the next chapter. Okay, we're going to now look at fuel consumption. So based on this graph here, you can see about 82% of fossil fuels, 82% of the energy used comes from combustion of fossil fuels. And fossil fuels is oil, natural gas, and coal. The combustion of fossil fuels produces CO2 in the air, which does have an effect on how we are living and watching what's happening with climate change. Natural fossil fuels also contain a small amount of sulfur. Sulfur that burns to produce SO2 gas, which then reacts with oxygen to form SO3. Why is this a big deal? Well, we'll cover that in the next slide. The high temperatures of combustion allow nitrogen in the air to combine with oxygen and also forms oxides of nitrogen. So if we skip over to that, we have natural and pollutant gases that are dissolved in the air, and they are CO2, SO2, and NO2. Now, nonmetal oxides are acidic. So this is what's playing into acid rain. So if we look here, CO2 combines with water and makes carbonic acid. If we look at the next one, the SO2 comes into contact with oxygen and water and produces sulfuric acid. And we have NO2, which comes into contact with oxygen and water and produces nitric acid. These processes produce nonmetal oxide gases as waste and increase the acidity of the rain. Why is this a big deal? Because these acids combine with water and form acid rain. That's a big problem. So if we look at here, we can see this is a hydrogen ion concentration, SpH. So you can see that this is a very big problem. If we look at this, we can see that this is really green over here, and that's the upper Midwest or upper portion of the United States. And you can see that the acid rain is significant. Then that's because of the sulfur and nitrogen oxides that's been produced by the coal combustion. So, and the wind carries it over to the northeast by natural air currents. So it travels. It's not staying exactly where it was produced, and it's traveling elsewhere. So why is this a big deal? Because acid rain is, first of all, it's acidic, and acid affects everything. If you've ever seen statues, that I think there's slides here, they just corrode the statues. They can hurt the trees. You know, these are signs of effects of acid rain. Water life. This acid falls somewhere, and if it falls into lakes, it now makes this water more acidic, and that affects aquatic life, and it could kill it. So acidity also causes more dissolving of minerals. These are big deals. So even in conditions of the ocean, if the ocean was to turn more acidic, this is a problem, because a lot of creatures that live in the ocean, they use calcium carbonate for their shells and so forth. And the more acidic it is, the more that dissolves. So there's a very big deal about concern about acid rain. So acid rain legislation, 1990, there was a Clean Air Act that attacked acid rain, which forced utilities to reduce the SO2 that was being produced. And that actually helped it stabilized, and it started to show processes of the acid rain being reduced. So what we put in the air really does matter, because even if you don't realize that it doesn't affect where you live, the wind can travel and take it elsewhere, and it could do severe damage. So if you look here, the air quality, you can see where SO2 in 1990s, concentrations of parts per billion, and it has gone down consistently since then. And that's a great thing. So the problem is, and this is where people get upset, and I'm not trying to be political here, but we pay, in California, we pay a lot of fees. And I'd like to believe, that's a key word, that when we pay for our smog emissions and we pay for this stuff, it's because they're trying to actively reduce the pollutants in the air. Now, I'm not going into that any further, but that's what I would like to believe. Have I done research to make sure that's true or not? I don't know. No, I haven't. So my belief, without any justification behind it, is that when I pay for this stuff, I believe that it is making an impact on decreasing the pollutants in the air. This sign here shows that whatever was done since 1990 has actively done that, and that's fantastic.